So the idea is the following. For some time, I was thinking about what is emergence in the physical world and this story that we have multi-level systems that is very pervasive. So in nature, we have all the different scales, and the idea is that at every level, it seems that there are their own rules, that they are autonomous, they don't depend on what is below. And this is, let's say this is a fact. How to frame this is another question, but let's say this is a starting point. So I was wondering, we have this other notion of abstraction. And in the case of abstraction, you have this person watching this object and is saying, oh, this is a spheric piece of bronze, and a sphere and bronze are different concepts that happen to be in this place. And it's sort of a coarse graining, or maybe not. And I was wondering, like, are these two things related in somehow? Is it possible to build a bridge between the abstractions in the physical and the abstractions in the mind of the observer? So this is the direction that I'm studying. I'm trying to see how much I can say about this in a formal way. So for this, the plan today, first I will talk about the emergence in the physical, the left side. Then a little bit about word modeling. What does it mean for an agent to have ideas about how the world works and how we can frame this mathematically? And then in the point three, we're going to combine both and see under what conditions the emergence in the world is reflected in emergence in the physical, in the word modeling of the agent. And then at the end, some takeaway messages. Okay, so that's the plan. How much time do I have? Like an hour?
An hour since you started talking.
Okay. So for the first part, the work done with wonderful collaborators and supported by Pips. So that presentation, first I will walk you through some ideas and then some consequences of those ideas. So this research started from asking what is software and when is software taking place? It's pretty clear when we design software in a computer, right? So we know that it's a laptop and has software, but is a rock rolling down the hill running software? That type of question. And for me, the key insight is that if you have a piece of code like this, and you say A equal B to B equal 3, C is equal A plus B print C, and you run it, you get a 5 in the screen. You run it again, you get a 5. You run it many times, you get a 5 every time. But the physics under which this computation is taking place is different every time you run the software, right? So software is not floating, it's instantiated in physics. And every time you run the computation is different, but at the coarse grain level is the same. So it seemed to be some type of decoupling between what is happening in the micro and what is happening in the macro. Of course, the macro is a simplification of the micro. There is nothing extra. But there is a level that is controllable in its own, because I can specify the thing I'm seeing in the screen from the inputs of A and B and nothing else. Now, let me try to convince you that toilets run software. And this is the idea. So every time you flush the toilet, the water goes out. And when the water goes out, the water starts coming back. And the level start rising, and there's a floating device that is down. Eventually, it's going to be pushed, and at some point, it's going to shut the input, and then it stops.
It's a while loop.
Exactly. That's a while loop. Although there is all type of turbulence and Navier-Stokes and all sort of things, but the while loop don't care about that. The while loop cares about the while loop. And the fact that there is a while loop is why we like toilets. I would not like a toilet that every time I flush it, I get a random thing, right? It's great that there is a consistent while loop happening every time. So, and my claim is that this happens everywhere. Like any agent, usually they have very coarse-grained sensory information. Like a self-driving car is not computing the wave function of the surroundings, right? Although the surroundings are quantum. But it's doing fine with that information. And we do the same. We don't compute the wave function. We have very coarse-grained inputs, and we find our way. We have jobs, we pay our taxes, etc. So this seems to be quite common, actually. Now, how can we formalize this a little bit? So the idea here is the notion of information closure. So we're going to have some time series process at the micro level X, over time. So this is a discrete time stochastic process. We have a coarse graining function that gives you a simplified version of it. And we're going to measure the ability to predict the future of the coarse grained future. So the number that you see on the screen, irrespectively of the underlying physics. And we're going to do this prediction in two ways. We're going to predict the future of the macro in terms of the past of the macro, and the future of the macro in terms of the past of the micro. And by information theory, this is always at least, is usually larger than this, but it could be equal in special circumstances because there is more information to predict. Than in information theory, this is ideal world, there's no fitting, information never hurts. So the idea here, information closure happens when there is a level that has everything it needs for optimal prediction. And the intuition here is if you would have to pay money to, let's say I'm a macro observer and I want to see, predict what will happen in my macro world in the future, and I can do that prediction with what I know, but there is a genie coming and saying, if you pay me money, I can give you micro information of your world. Should you pay that money? If you shouldn't pay that money, that means it's informationally close because the information would be wasted. There's more information, but it's not relevant for the macro. And that means that the macro has everything it needs to predict itself. And in that sense, it's informationally self-contained. Now, how can we push? So this is an old idea that have been studied in different contexts. My interest at this point was to study this from a more computational perspective. So this is prediction, but could we say something about computation? And here I took inspiration in the work from Jim Crutchfield and collaborators on computational mechanics. For people that are not familiar, there is a key notion known as the epsilon machine of a process. And the idea is the following. You have a time series data. Let's say this is a micro that's doing something. And there is a canonical way to build a latent process that is generating what you observe. There's a hidden Markov process on HMM. And there is a canonical way to build a minimal HMM. And the intuition, more or less, is that the hidden process is like the mechanism, what is like the inner workings of whatever, and then the inner process is generating something that I observe. So it's a way to attribute some type of computational process that happened behind the scenes that explain the data that I observe. So this is the basic idea of and for this you do coarse graining on histories. So you take histories and to the degree they predict the same in the future, you coarse grain them and you do it and you get an HMM. So I will not get into the details. The sort of the picture is we're building this hidden process that explain my observations. Now, what is interesting about computational mechanics is that this HMM is very specific, has specific properties that let you flip it and see it as a stochastic, as an automata. So for you that are familiar with theoretical computer science, semi-automata, to be precise, is a machine that has a state and you put an input and it updates to another state and you put another input and go to another state and then you start having deterministic dynamics between states driven by inputs. And this is a very different perspective from the one below. The one below is more dynamical systems. So there's something happening, and then I see something. The other is more computational. Like you have a string, an input string that you put out of your pocket, and you put it in, and the thing is doing some dynamics, and how it moves through the states for a given string tells you something interesting about what is happening. And this duality is what I found particularly interesting that is given by the epsilon machine. You can see the same process from a dynamical perspective or from this computational description.
Here, the bottom is a stochastic process.
Yes.
The top is completely deterministic.
Yes. And another sort of funny thing is that here the data is sort of generated by the process, and here the data is free. So you fix it. And the game is that you try any possible input and you see how the dynamics move between states. It's not the other, you are receiving the data. So the arrows are almost the opposite. This is just description. These are different ways of talking about the same process.
I've heard people refer to the top thing as an edge emitting automaton, where you interpret this emitting this token.
I think that is edge emitting HMM. Because this automata is technically not emitting anything. It's a semi-automata, so it has inputs, but it doesn't have outputs. And the inputs is what drives the transitions. But yeah, in the paper we try to do some, and the another paper we try, because there is a lot of terminology from dynamical systems and HMM and from automata that are actually contradictory sometimes. So it's a bit of
The inputs determine which edge you follow.
yes, exactly. Yeah. And then the question was, if we have this canonical way to build machines to explain data at different levels of resolution, And let's call this machine a theory. So this machine is sort of explaining my data. And I can build these theories at different scales. How are these machines going to relate to each other? That was an initial question. And naively, in the beginning, I thought, well, the machine should become simpler, right? Because the data is becoming simpler. I'm just coarse graining stuff. So then I'm keeping less computations. And the answer is this is not true. In general, as you coarse grain, the machines become more complicated. Why is that? One way of thinking of it is that, let's say you have a macro process in the micro. So the machine is actually very simple because machines are usually taking into account the memory of the process. And if the process in the micro is macro, you coarse grain in a random way, and the coarse grain version is not Markov. So the macro is not Markov anymore. And that will make the memory very complicated. And for explaining that memory full non-Markovian process, you need a more complicated machine. So usually when you coarse grain, the machine becomes worse. Now, the interesting case is when machines become simple. And this can be framed here intuitively as like a bit of a matryoshka. So here you have a machine with small states and arrows, and then there is a way to make bigger states such that there is a way to coarse grain the inputs also that correspond to all the small arrows. So you get less also arrows, and the whole thing is consistent. You can frame this very formally with automata homomorphisms, so your mapping states, your mapping transitions, commuting diagrams, all sort of things. But the intuition is that you have a machine that is a simpler version of the original one, and they are nested in a nice way. And this is what we define as computational closure. And computational closure means basically that this commuting diagram commutes, this diagram commutes, so you have two ways to build theories. Here you first coarse grain your data, and then you build your theory, or here you build your theory and then you coarse grain your theory. And there is a way to arrive to the same point. And I like thinking of quantum mechanics here and classical mechanics. So you could have quantum data, you could get quantum mechanics, or you have quantum data, coarse grain, you have classical data, you build classical physics, and the theories are also compatible.
There's additional parameterization.
Yeah, I mean, I would like to know. That is yeah. And this is sort of how the picture looks. So you have this more fine automata, and then you coarse grain it. So you're merging these two states, and then you're merging again. So you can have different machines. Not every coarse graining is computationally close. And this we will call, these are the good coarse grainings because they simplify the computations. Let me give you an example to ground this a bit. So here we have a network fully connected with different weights. So strong connections within communities and weak connections between communities. And we're going to have a random walk. You start randomly, and then it moves to another point proportional to the weights of the links. So what happened here, you are going to move between your community, and sometimes you will switch, and then you move here, and then you switch, like that. So the first coarse graining you can do is to coarse grain to keep only the communities and claim, you can prove because of the symmetry of this underlying graph, this is going to be computationally close. And you can coarse grain again, and now you keep only the size of the community. So I'm in a community of size 25 or size 9. And the claim again is that this is also computationally close. So basically, one idea I like thinking, if you want to simulate this data, you could first simulate what is my next size of my community. So I'm jumping to a community of size 25. Then you say within the community of size 25, I'm going to this community. And then within this community, I'm going to this node. So you could update your state in this hierarchical way. And you can do that because of computational closure. Good. So this is an example to kind of ground the ideas. Now, yeah.
So, I might also think of just a vanilla random walk. If I coarse grain in space and make some assumptions about the scale of, if I coarse grain in space, I should get the diffusion equation. So does that come, that's a kind of quirk
Yeah.
I understand.
I know, but
Does that come out of this process?
no. So if you have a uniform graph in 1D
Yeah.
diffusion, I don't know how to coarse grain to get a computationally close process. Because you know more. Like if you're coarse graining groups of 3, you know more if you're in the edges than if you're in the center. So This is perfect closure, like we can try to think
So
more.
then I'm wondering whether there's a part of this that I don't get, which is that you have to throw, I mean, for examples like this diffusion equation, do I have to throw away, so is I'm looking for a non-perfect coarse graining or something, I throw away information or something.
But the diffusion is tricky because you have first a discrete description, I
Yeah.
have a continuous one. So is it simpler?
That's why I'm asking. Okay.
Yes,
Related to this, I guess this depends on the modularity of your.
100%. And the symmetry, like if the weights are not exactly the same, then the thing breaks.
So if you push the modularity to kind of 0, then it becomes a completely this case, and you push it to complete, then it's just the top description is perfect, right?
Yeah. But this is not a
Yeah, okay.
but this is not a general statement about random walks. This works here for this very specific construction. And as soon as you break the symmetries and this is not perfect, this is be close to close, almost close, but not really. Okay. So
So all the things you're presenting you don't have any example in which it sort of applies to thermodynamics or something?
yes, I have one. It's coming.
Okay, but not diffusion.
Yeah. It's some type of diffusion. Let me. So now the implications. So far, just some bit in definition. So what are the implications and some examples? So the first implication, one could ask, what is the relationship between computational closure and information closure? And as the theorem says, information closure implies computational closure. So being optimally predicted on yourself is stronger than this computational thing. And the kind of the master plan is you have the graph of the lattice of all coarse grainings. You keep only the informationally close coarse grainings, which is good. Now you have every level that explains itself. But now every level of this you can represent with an automata. And all of these automata are coarse grainings of the micro one. So now you have a coarse graining, a lattice of automata. And sometimes you will have different processes in the way they look, but computationally they will be equivalent. For example, if you have a coarse graining that gives you an IID process, that the automata that correspond to it is a single state that goes to itself because it's not doing any computation. And it's the same automata that you coarse grain to get the constant. So there are many cases where processes look different, but computationally they are equivalent, so they're going to coarse grain the same lattice. And my claim is that this lattice is the hierarchical computations that are happening in the system. Now, let me give some examples. One from thermodynamics. This is a very classic diffusion model. This is very simple, the Ehrenfest diffusion model. So you have gas particles between two chambers. You have the microstate is a binary vector. And the dynamics are at every time point you pick one particle, and there's a probability in which you flip it to the other chamber. That's it. Very simple. And what happens if you simulate this, you start here, this is a 40 particle system, you start with 35. Very quickly, we'll thermalize around 20 and then start fluctuating around the middle. Okay? And the claim here is that the number of particles in one of the chambers is informationally close and computationally close, and the whole thing. What do that mean? What is the meaning of that? It means that the underlying process is Markov. In this particular case, if is a micro Markov, every computational close is also Markov. So the dynamics of the number of particles are also Markov. And the interesting point here is that if you figure out the Markov dynamics of the number of particles, you can simulate the number of particles perfectly. So this simulation is not an approximation of what will happen if you simulate the whole thing and then you coarse grain. The simulation is absolutely perfect. So in an agent-based modeling kind of mindset, you could say, no, I want to run everything because I want to have perfection. But when you have computationally closed levels, when you simulate only at that level, the simulation is perfect because you're not leaving out anything relevant for that scale.
Is there any assumption about large n?
About what?
Large n,
No, not at
you
all.
don't need a large number of particles.
The only important assumption that will come at the end of the talk is symmetry. So the particles are exchangeable. In this case, they're not interacting, but that's not important. What is important is that the particles themselves, you can exchange them and the dynamics are equivalent. And given that, the orbits are close.
I thought you wanted to simulate two levels and check that they are equivalent, right? So you wanted to simulate in the macro level, see that you can predict your future. You need to simulate in the micro level and see that you can
I would not do
In the
it.
future,
I would not do it with two simulations. I would do the same simulation and then with the same information of the same simulation at two levels, you try to do the prediction.
Huh.
And then it so happens that by knowing which particles are where, you don't have a better prediction of how many particles there will be in the right in the next times.
But is that what you've done here? or-
Yeah.
So there's two different simulations?
No, one simulation. But I mean, I didn't. You can't just prove this theoretically. You don't need to do simulation. Yes.
There's a funny thing which you can do is if you find a computational closed level like this and say I want to actually simulate the Ehrenfest diffusion model at microscopically,
Mhm.
I could take a shortcut by going to the computationally closed level, simulating that,
Yes.
and then go down again.
Yes.
But that going down is actually is not usually part of the computational mechanics framework.
No.
Right? It's sort of a D-course grading.
Yeah.
It's a sort of principled way to say how you should do that.
It's a bit of a. We can. I think there is, but I have never seen it explored, and I would find very interesting to see the computational complexity of that because
Yeah,
I
exactly.
would presume that maybe you can do it more efficiently, but that sounds like a free lunch, so I'm not sure.
Yeah, exactly.
Mm.
But I mean, there cannot be a unique way of going down.
No, exactly. But there can be sort of the
There should.
right way.
Yeah.
There's certainly a wrong way to do it. But there's also, right, in this case, you would uniformly sample the particles in the box.
But no, but you have to take into account the previous state.
Right.
So it's a bit tricky.
Yeah.
No, but that's I've been thinking about that, but I don't know exactly how to explore it. But that's yeah. Yeah. So this is an example from thermodynamics. One example from computational neuroscience. This is called the Hopfield network. I guess you're familiar at this point with Hopfield networks. So Hopfield network, you have a recurrent neural network. And in the weights, you encode patterns such that you have these attractors that pull the dynamics to retrieve those memories. So here you have a network that learned these 5 digits, and depending on the initial condition, it will end up in one of the 5, here most likely in number 2. So the claim here is that there is something called Mathieu potentials, this set that are direct dot products between the candidate destinations and the current configuration. And you can prove mathematically that the vector of these potentials is computationally closed. And the implication of this is that if you want to know where the system is going to end, you only need to read these potentials. You don't need to know anything else. Like the retrieval doesn't happen at the neural level, it happens at the level of these potentials. Another way to put it, if I exchange my initial conditions in a way that the particles that are, the neurons that are firing are different, but the potentials are the same, the destination, the probabilities of destinations are exactly the same. And one example of ongoing work, I've been simulating data from this process at this level, and then I take a transformer to learn how to predict this process. And I ask, there is a way to track predictions at this level, and this level. And what is interesting is that if the transformer is large enough, it will learn the 3 scales. If the transformer is not large enough, so it cannot learn the micro scale, it will still learn the macro scales. So it seems that the transformer is figuring out that there is these abstractions, these levels of abstraction that you can, although it's like, okay, I cannot do the whole thing, it's just too complicated, but I could predict this part of the system and I could really do it. And it does find those things. And you are not telling anything about the transformer about how to do it coarse graining. So this is very encouraging that maybe some AI systems are finding naturally this coarse grainings. But this is one example and ongoing work we are doing to see if this replicates. So as a summary, hierarchical emergence is this idea that you have levels of a system that are computationally autonomous. What is good about these levels is that you can either control them efficiently only at that level, or also you can simulate them if you want to study systems without bothering checking below. This hierarchical emergence happens in some statistical mechanics and computational neuroscience models, and transformers seem to naturally identify these levels. So this is how we're thinking about hierarchical emergence in the physical. Now, how do we think about work model.
Just to, you're gonna move on to another section, so. How close is this aligned to coarse graining that we're used to doing in physical theories? I mean, you gave some examples where you think it's the same.
Mhm.
But what about other examples? Like, are there cases where, like, that's why I asked about the diffusion, but what about other examples? Like, how closely do you think this aligns to what we?
I think it's not very close. I would like to know. So the honest answer is that I have been learning randomization on the process of doing this. I did this work because I wanted to have a randomization that I felt it was more directly applicable in neuroscience. Because there is some dynamical randomization, but I found it very complicated. And so I developed this thing, and at the same time, I've been trying to learn about randomization, but I don't know so much, and I'm trying to build the connection, but they don't seem to be very straightforward. Like, for example, the classical thing, you have an Ising model, you're coarse graining to get another Ising model. I don't think those coarse grainings are computationally close. There's a lot of approximations and things. And also in a lot of the theories, you have infinite systems that you have to coordinate. This all works in finite systems, that it was something that I wanted to. So I'm very interested to learn more about that question.
There's also this weird, what we discussed yesterday, there's a weird difference in the conceptually between coarse graining states or variables. Where here you have states, but you don't know how these states correspond to configurations of some variables. Right? Just every state here could be like an individual configuration of an Ising model, which wouldn't see how many spins there are.
Yeah. And maybe also the criteria for convex, because you normalize infinite systems and you see a fixed point approaching. And for Fernando say, you would need to create a criteria to stop when you reach a macro level. And then it'd be a finite process. You don't need to have a infinite process.
Another thing that I also find quite interesting is that what I will present in the third part is telling you that the symmetries tell you which are the coarse grainings. And from what I know in randomization, usually the coarse graining, you find them because you're lucky or you're smart. But I don't think there's a principal way to find the right coarse graining. So that's another thing I would like to know better, like how these things relate. So let's switch gears to word modeling. And then we're going to come back to all of this story of hierarchical emergence. So this worked with other colleagues and supported by Arya and also Pips. So first, some basic setting, description, and foundational ideas, then some ideas about minimality, and then interpretability. So what is the setting now? The setting is that somebody builds a robot and gives it to you. You have no idea how it was built, and you want to test it before deployment to check that it's safe. And the plan to test it is not to throw it away and let it go around and do whatever it wants, is to build a simulator. It's like in the Matrix. You want to put the robot in the Matrix. So you build an environment, a virtual environment for the robot. So the robot does things and then observes things as a result of the actions. So you want to build a virtual environment that takes the actions as inputs and generate perceptions to the robot, such that the environment is sort of the same thing that the robot will encounter in reality. And once you have that, you can sandbox the situation, you can let the robot do things, and then you can check if it's safe or not. This is a problem setting. Now, let's say we can do it, but maybe there are issues, like maybe we can simulate the whole planet at the quantum level. That would be a great model, right? But it's a bit computationally expensive. And every time we run a simulation, we will be burning, the whole Amazonas. So how can we compress the word model? Then maybe also same idea, like the agent might not see some resolution. Maybe you don't need to simulate the quantum. So maybe you can coarse grain. Or maybe the agent is only living in a room and is not going to the next room. So you can also spatially limit the world. So as an inspiration, have you heard of the brain of bat? This is a thought experiment from the philosophy of mind literature. So the idea here is that you take a human brain, this is a thought experiment, you put it into a vat, you read the motor cortex, you put it into a computer, the computer does some processing and generates some inputs to the sensory cortex. And the story goes, if you do this in the right way, the brain will not be able to tell the difference from reality and a simulation. And there's a whole story, a lot of discussions on this. This is possible, it's not possible, is the brain a computer or not, blah, blah. Not going to neuroscience, the idea here is to do the same with an AI system, so the same idea. And the question is how to do it. And I find interesting this question for two reasons. One is a computational question, like how can you do that in the most efficient way? So if this could become one day a scalable and affordable way to do it in practice, efficiency would be very important. So what is the minimal world that you need to simulate, like the minimal set of computations you need to simulate in order to have a veridical simulation? But the more important, interesting question I find is that by finding this minimal world, you can tell what the agent can see in a way. And you can assess the level of how capable it is. Because a capable robot will require a very complicated world. A very incapable robot maybe needs one bit of information, like a switch. So by knowing the complexity of the minimal world that a robot requires, will tell you something about how smart or capable the robot can be. Now, how can we do this formally? This is all theoretical. So the starting point, we're going to call something the interface of an agent. And the interface of an agent, we say the agent has actions A and observations Y. So the interface is a collection of conditional distributions. These are sequences from 0 to t, when there is nothing here from 0 to infinity. So this is all type of conditional probabilities of, for a given sequence of actions, what is the probability of observing a sequence of observations? And the idea is that this is how the world looks from inside the agent. The agent has no idea about the world. It can only see some stuff as consequence of the actions. And these probabilities are encoding all those things. As a graphical model, this looks like this. For a given sequence of actions, you generate a sequence of consequences that the agent can perceive. Now, what is a word model? And this is a definition. A Markov word model for a given interface is another process, S, that the agent is just inventing out of the blue. But the key point here is that this graphical model is completely incomputable, right? Because as the sequence grows, you have more things. So it is a matrix that is growing exponentially when you consider longer and longer sequences. If you have a way to build a process S such that you have a graphical model factorization like this is working like a sufficient statistic, right? So for example, if the agent needs to consider, what if I do this? What is the consequence for what I would see as a consequence of that action? This action perception loop has a memory, because depending what you did before, that will affect what you observe. But all of that previous information is encoded on the current state of the world. And this blankets out everything that happened before from what will happen after. So a word model is a third process that you believe on. You can create it out of the blue, such that you can factor things like this. And then this conditional probability, that in principle is very intimidating, it becomes a sequential computation of some kernel. And then this kernel is what makes the agent possible to estimate probabilities and plan, etc., etc. So basically, the word model is a process that you built such that the computations become scalable. And what is interesting, this tells you that there are many words models for a given interface. So an agent can believe in many worlds that could explain what is perceiving. And these word models can be understood as transducers, like stochastic automata. And here this means that you have a state S, that is the state of the world. You do an action that updates the state of the world and also generates an output, and then you make a second action. So this has a direct connection with the work from before, right? And this is how we're going to eventually connect it. Now, just to sort of get more intuition on this, when could I say my interface, I would think the world is trivial, like a constant? Is that possible? And the answer is only if your interface is memoryless. So if everything you see is a consequence only on the action you did at that time, but nothing before, so there's no memory, then you can prove this word model works. If your interface doesn't factorize like this, then it doesn't work. The world has to be more complicated than that. When could the world be just what I observe? I could say the world is fully observable. Whatever I'm observing, that's the world. Only if the interface is Markov. So everything that affects the future from the past is just the previous thing. So there is a number of interesting things you can see. And the main consequence is that the world model, the transducer, is capturing the memory in the perception action loop. Another thing that is interesting, this model of transducers as world models are summarizing a lot of different constructions from the literature. So for people that are familiar with reinforcement learning, POMDPs are a specific type of transducers. There are two types of POMDPs depending on how you index the time. So if the action happened before the observation, you have this arrow. If the action happened first if the observation happened first and the action happened later with the same time index, then you don't have this arrow. What is more interesting from my perspective is this arrow that doesn't exist in POMDPs. That means whatever I observe don't affect how the world evolves. And that's sort of a classical physics perspective. Like what I observe is not affecting the world. In a belief model, in a model of beliefs, you want this arrow to be there by all means, because it means what I observe is affecting the change of the world. And then the world might not be necessarily a physical representation of the physics. Maybe it's a representation of what you believe. And then there is a whole story about belief NDPs and belief updating, and all of that can also be captured by transducers. So this is a very general construction that special cases happen by cutting some connections. Yes.
So the difference between a full transducer and a belief transducer is also just time index.
No. Between a full transducer and belief transducer is the absence of this arrow that is not a consequence of time index. The difference between these two types of POMDPs is a time index. But you cannot get from here to here by changing time indexes. This is the difference between sorry, I get your point, your question now. I have to think about it.
It seems like it.
Could be. Yeah. Yeah, what I was saying is the difference between this side and this side.
Yeah, sure.
Yeah, you're right. Yeah, maybe. But for me, the more important thing is that arrow existing or not. And that tells you this is a physical world model or this is a psychological world model. And I will explain much more in detail the implications of this. Now, what about minimality? How can we build a minimal world model for a perception action loop? So first question, for a given interface, can we always find a transducer for it? Maybe there are some interfaces that are so evil that there's no world model for them. And the answer is yes, there is always at least one transducer, which is a bit trivial. You say the world is everything that have ever happened. We call this Funes from Borges that had the story of this guy that couldn't forget anything. So the idea is that if you keep everything in memory of everything that ever happened, that factorizes the graphical model and works formally. It's not very efficient because the word model, this phase space start growing exponentially, so you're not gaining anything. But at least formally, you can say every transducer has at least one word model. Now, it's not very efficient. So now we can turn the question of minimization to the question of reduction. For a given word model, how can we compress it? And a word model reduction is a coarse graining function that goes from here, and you compress the phase space of the word into something smaller. So you're identifying states of the word, and the requirement is that despite the compression, this factorization still holds. There are many such coarse grainings that are going to break the factorization. But if it doesn't break, then this is a valid world reduction. All right? And then from the notion of world reduction, you can define what is an isomorphic world. So you have a world and you compress it, and then you compress the second world and go back to the first one. You're just relabeling. You're not really merging anything, right? So you can define isomorphism, and you can also define minimality. So minimality means you reduce up to a point that every reduction is isomorphic to yourself. You cannot reduce to something non-isomorphic. So at this point, question for people. If I have a given interface and I take two world models as starting points of reductions, and I reduce as much as I can, am I going to get to the same point or not? And of course, I'm asking because the answer is no. But that I was very unhappy when I found that. So it so happens that word reduction leads to minimality, but minimality is not unique. And it's not unique up to isomorphism or anything. So sometimes you will get an endpoint that has different number of states from the endpoint you get from a different starting point. And that's very unsatisfying, right? The reason why this happens, I can give an insight. So reduction is about collapsing states. And you can do, for example, there is a matrix that is pretty famous in this literature that for a given initial condition in a word model, you compute probabilities of future things happening, which is sort of a vector. And then you can compute this vector of probabilities of future events for every initial condition of the world. So reduction means there are some of these vectors that are the same, and I can compress it. But what if I have three vectors that are not the same, but they are linearly dependent? That feels redundant, but you cannot get rid of that redundancy with coarse grainings. So what can you do at this point? Either you accept that the world is a sad place, or you embrace negative probabilities. And what is that? How can that be? So the way it works is the following. This is not anything. This is quasi-probabilities. These are vectors that can have negative terms, but they sum up to one. So for example, here we have a quasi-flip coin. So if you coarse grain this vector, if you coarse grain these two things, you get a fair coin. Suddenly you cannot identify these two events, you get a fair coin. If you coarse grain these two events, you get an unfair coin. And you cannot observe the whole thing because you cannot sample that thing. There is no law of large numbers or anything. So I like thinking of this a bit like quantum things because you cannot observe them, but they can be coarse grained to things that you can observe. Now, why is this useful? The thing is that the minimization of the word model, you have some equation like this, and you're minimizing these objects in between, these matrices. And it so happens that if you put a restriction that the items in the matrix are non-negative, you have less solutions, you have more solutions if you don't have that restriction. So it's not very mind-blowing that if you allow negative probabilities, you can have rotations, and they have to do with these three vectors that are dependent, but not identical. So if you allow rotating transition probability matrices, you can find a unique word model that is minimal. So what is the limitation? You cannot observe the word. So you can have now a quasi-stochastic process that generates your interface. So you could use it to simulate the sensory input to your robot. And it's going to be the most efficient way of doing it, in the sense that the computation will have smaller matrices. However, you cannot interpret that thing. You cannot say, oh, the world was doing this and then jump to that, and because of that, the agent do that. You have no idea. You cannot reason statistically about the world. So in the way I see it, there is this trade-off between efficiency and interpretability. If you want the maximally efficient simulator, it's going to be a black box. It's going to get the right probabilities, but you cannot reason about it. If you want something more interpretable, you cannot be so efficient. So this is about minimality. Now about interpretability. What makes so we know now that if you want the ultimately more sufficient word model, you get this negative thing. But what if we restrict the word model to things that the agent could learn online, on the fly? And for that, we can make two assumptions. The first is that the world is observable, not fully observable as before, just observable. That means that the state of the world is a function of the history. So that means if the agent is smart enough, it could compute the state of the world. It might be a complicated function, it's not keeping everything in mind, but there is this function. And another assumption we could make is that the world is unifilar. And that means that to update the state of the world, I don't need to recompute this function from the beginning of the universe, but I need to know the previous state and the next inputs, and there is a smart update that gives me the next state. So unifilar worlds are nice. And this is what you would like to have as an agent, because it's something you can compute for yourself, and it's something that you can efficiently update. How can we create these unifilar worlds? And this is the idea of beliefs. And to people that are familiar with Bayesian beliefs, so you can have a history, you build the posterior distribution of the states of the world that you think there could be given the history. And then if you get more information that is based on updating, that you take your previous belief, your new information, you update, you get a new belief. And this, you can prove this is a world model that is unifilar. Now, the most interesting part of the story, this is not shocking, I would say, right? We can build Bayesian unifilar worlds with Bayesian updating. The most interesting stuff is that there is something similar to the epsilon machine. It's called the epsilon transducer. It's a bit more complicated because you have more conditioning of the actions and things, but the basic idea is the same. You have histories that are equivalent to the degree that they predict the same future observations for some future actions. And there are a number of super interesting implications of this epsilon transducer. The first is that you can compress the fullness and you get this. This is not super surprising. What is very surprising is that any world model that is observable, and you can generalize a bit more, but let's think of observable. Any world model that is observable, you can coarse grain it to the epsilon transducer. And because of that is the minimal world that generates the interface that is predictable. So what is the meaning of this? Let's say I'm a human, I have a given type of interface. There is this other human that has the same type of interface, but I believe in a weird religion, and this other person believes in another weird religion. So we don't agree on what is happening. But the claim is there is this minimal world that explains our both interfaces because it's the same interface, and whatever we believe can be coarse-grained to that explanation. So this is something any agent with the same interface has to agree upon. And whatever your world model is that plus something else. So that's what that, and
So how do you get away without negative probabilities now? You find a uniqueness.
because the negative probabilities is the minimal world model between all world models. Now we're saying we are restricting ourselves to observable and not unifilar. We are restricting to observables, and within all the observable world models, there is one unique. That and basically this picture doesn't happen. Everything converts to the same. Is it good? So to conclude this part, first take-home message from this part is that the class of world models for a given interface is very rich. In the beginning, I thought, oh, maybe there's one or maybe there's two, but there's no trade-offs. I thought there should be something that's optimal, but no, it's very rich. We have this intrinsic trade-off between interpretability and compression. And for the case of online worlds, there is this unique solution that is optimal, that is Bayesian updating. And I have always been on the skeptic part of on Bayes, because people say Bayes is optimal. Optimal for what? Like I never got a good explanation. What is the optimality of Bayes? And here there's a very clear example that Bayesian updating is optimal for minimal worlds that are observable, so computable for the agent. So any agent that wants to explain what is going on in his perception action loop or her perception action loop is optimal to do Bayesian updating. And so I thought it's a very strong result. Yes.
Very vague question. For the first time I listened to the word for the negative probability of quantum mechanics. In analogy.
So these are not the probability amplitudes. So this is not the same as a quantum, but there is not so much work on quasi-probabilities. So the literature on minimization of HMMs and these things, they have these quasi-probabilities, but there are like, I don't know, like 6 papers. They're awesome, they're incredible, but nobody cares about them. So it's a very small community and very close. Yes.
So provocative idea that I probably don't believe in myself. But does that mean if you train a transformer on a non-observable simulation of a non-observable world, that it would be better if you don't impose softmaxes everywhere? You don't enforce it to think in terms of probability.
I'm not sure, because the transformer has to build a thing based on the past. So it's restricted to observable things.
Okay, right.
So
right.
If you do a transformer that can do like a forward and backward prediction or something like that, maybe. Yeah.
Without softmax.
Yeah, yeah, but not for like with the causality thing.
Right.
So now we are ready to the final and most exciting part. That is, let's combine these ideas. So, and the combination, I take inspiration on cybernetics. Are you all familiar with cybernetics? So, cybernetic was this sort of megalomaniac world domination idea in the beginning of the 20th century that they were going to unify everything and everything was going to be great. Uh, it sort of fall apart. It brought the seeds for a lot of things that we love today, but the whole Unify project fell apart. Now, I feel there are very, very good ideas still in cybernetics. For example, one of them is this principle of recursive variety that say a controller needs to be at least as rich as what it wants to be controlled. Or the good regulator theorem that say the good controller needs to have a model of the target. And the problem is that some of these things are wrong, or the math is a bit weird. So there's endless discussions about all of these results. But I take home this idea that I find very interesting. Like, to what degree the agent believes the word modeling of an agent has to reproduce structures from the world. So this is a sort of a general question that I take as an inspiration from cybernetics, but I'm trying to pursue in a different way. And specifically, the question I want to explore here is, if you have a physical process that have all these computationally closed levels, to what degree that is going to affect the Bayesian belief updating of an optimal observer? And are the beliefs going to have the similar type of computationally closed thing? And the answer is yes. So what is the idea? And symmetry is going to be our way in. So do you know all the difference between invariance and equivariance? Maybe, maybe not. So the difference is invariance is you have two values here, and they are related by some group, so they are symmetric. And then you apply a function and you get to the same point. So you say this function is invariant to the action of the symmetry. Equivariance is a bit more complicated. You say there is a symmetry in the inputs, you have this function, and they don't get to the same point, but you get to different points that are symmetric with respect to the same group. So equivariance is that inputs and outputs have to be adjusted. Invariance is only the inputs need to be adjusted. And we use this idea for dynamics. So invariant dynamics would be you have two initial configurations that are symmetric. Let's say, for example, you have the Ehrenfest, you have the gas particles, and you exchange particles. So that could be a symmetry, permutation of particles. So you have initial conditions, you let it run, and if they end in the same point, that will be an invariant dynamic to that symmetry. But if they end up in different points, but is the same point if you exchange back the particles, that's equivariant dynamics. Is that clear? So you exchange something in the beginning, you let it run, and you exchange it back, you go to the same point that you would have arrived. Of course, with stochastic process, you only can have equivariance at the level of probabilities. So you say, if I have this configuration, the probability of getting here is the same if I flip both of them and use this as initial and this as end. The probabilities are the same. So first result is that a dynamical equivariance is sufficient for information closure. What is the meaning of this? This is an example. We have here a Markov process with 6 states. And the probabilities are such that you have all the invariances of a D3 group. So you can rotate like this, you can rotate like this, you can rotate like this. All of these are invariances, equivariances of the process. So you can change states, you run the thing, and everything stays the same. Now the theorem says, because of those symmetries, you have the symmetry groups, every symmetry has orbits. And orbits are the things that, for example, if I'm considering this symmetry, that means that I can collapse these two states and these two states. And the orbits are the coarse graining that correspond to the symmetry. And the claim is that those coarse grainings are informationally close. So for example, here, if I apply all the symmetries to here, I end up with only two types of states, the squares and the rhomboids and the squares. Now I have a process between two states, and the claim is that this coarse graining is informationally close with respect to the micro. And the same if I rotate like this reflection, I end up with this separation, this type of dynamics, and that's also informationally close, and all of these are informationally close. So the beauty of this result is that symmetries at the micro level tells you not only one informationally close level, but a lot of them based on the subgroups of the symmetry. And maybe the lattice of subgroups don't reproduce exactly the same. Sometimes you have some collapse. So for example, here, the symmetry you get by pure rotations is the same that you get with rotations and all the reflections, so you get less. But it's a homomorphism between lattices. So this is the basic connection between symmetries in the dynamics and informational flows. As an example, the Hopfield story. Now we can revisit a bit with this idea. So as I said before, you have these matrix potentials, and you can prove easily that the dynamics are symmetric to, sorry, the matrices are the orbits of symmetries of the dynamics. Now, what I find very interesting, let's say now that there are symmetries in the training data. So we are learning patterns, but the patterns are 3 letters and all their rotations and reflections. So that's going to create more symmetries. And because of that, now the informationally closed levels of the Hopf field are more than before. So you can first go to the magnetization, but now you can for example, factor out the reflections and keep the rotations, or you can factor out the rotations and keep the reflections, or you can factor out the whole thing. If you factor everything, you're just tracking which letter gets retrieved. I don't care about the reflections. I factor those out. And I'm just tracking which letter is being retrieved by the process. And one thing that I find very exciting is still to be explored, but here we have compositionality by design. And that compositionality corresponds with the branching of the informationally closed levels. So could you go the other way back? When you don't know the compositionality of your structure, could you check how wide the informationally closed levels are, and from then infer back compositionality?
What do you mean with we have composition?
In the sense that to generate the training data, you can think, oh, these are rotations plus, so there's a compositional way to expand your data to so the symmetries are related to that. Yeah. So that is that. And now how this works with the belief update. And here there is another theorem that says the following. If the physical process, here we have an HMM that has symmetries in the hidden dynamics and the same symmetries with the measurements. So you have some process that has symmetries like this, and you get measurements, but the measurements are also, the relationship between this and the measurements is also equivariant. For example, you're measuring 2 particles and you measure each of them separately with some error, and the probability of seeing what I observe, now I switch the particles and I switch the measurement and the same probability. So there's equivalence in the dynamics and in the measurements. The claim is if that is the case, then you can do belief updating of the micro. So, and this is going to be a very high dimensional belief because here is 6 states only. So you have some belief on some 6 states, you get the new noisy observation and you update your beliefs, or you can have beliefs of the coarse grain level. And the claim is that you can do belief updating on this alone without taking care of this thing. And this is not true in general. If you have a Bayesian belief, very high dimensional, you cannot coarse graining in a random way and start updating it. It will not work. Usually that's not Markovian anymore. There's no way to update it. It's going to be a disaster. But this is telling you, if the process is coming from this HMM with symmetries, there is a way to track only the coarse grain level of the HMM with coarse grain level measurements. Let me give you an example of this. So again, the RFS model. So we have levels in the physics, and we're going to have measurements, and we're going to say that the measurement has error per particle. So we're measuring every particle, but the probability of error, we can make a mistake in the measurement with some probability. All the errors are IID. And because of that, there is equivariance in the measurements. So we have equivariance in the dynamics because the particles are non-interacting, and we have equivariance in the measurements. Because of that, the theory works. And what does it say? The theory says the following. Let's say these are my measurements. I don't know initial condition, uniform, I have no idea what is going on. I measure this thing. And based on this thing, I can build Bayesian belief on every state of the system. These are 8 spins. eight particle things. So I have 256 states. So I have to 250 something dimensional vector. I can compute all those probabilities, and then I measure this, and I update my beliefs, and I have this vector that I'm updating state by state. A very complicated vector. This works because they are 8 particles. If I have like 50 particles, forget it. In the paper I did the calculation, it takes like 1,000 years or something, completely ridiculous. Now, from this, I can estimate the number of particles in the first chamber, which would be 7. And then I have this belief that there are 7. Of course, because I had no idea in the beginning, and I know this is a noisy measurement, I'm not sure that there are 7. This is a most likely guess. But there I have a belief on the number. And now I can start updating this belief. And the claim is, I coarse grain my data, I have coarse grain data, and I just update my belief with this coarse grain data on the coarse grain belief, and that works. So you can do exact belief updating on this coarse grain level of the physics with this coarse grain data, and it works. So and that is what hierarchical belief updating means in this sense. Is it clear, the example?
I guess here it's even clear how to do the d-coarse grading, because you would go to the max end over all ones that are compatible with each other.
But the history matters. It's more complicated because if you measure this and this, then to decorrelate this is not like max end on everything with 6 states. It depends that you saw this before and you're seeing this. So this is likely to be right because you have seen this particle and this 2 times. So it's a bit complicated.
So here this works well because they are invariant in a permutation in the particle.
Equivalent.
Equivalent.
Yes. I have to say the paper is based on equivariance because it's a very clean story and very nice. The equivariance is not necessary; it's sufficient. So there are ways to relax this a little bit to make it more general. But I didn't do it in this paper because the story was going to be more complicated. But with equivariance, with the dynamics and observation, this is sufficient for having this story and having this belief that you can update at different degrees of resolution. But there might be ways to relax this a little bit.
In machine learning, you often have this spatial equivariance. So what kind of coarse graining would be associated with it?
The orbits.
Where?
So every point that you can rotate will be one state.
That's what you did in the letters just before, right? In the numbers.
Yes. For example, here, the symmetry is permutation. So you have one. Let's say you have this vector, and you can permute any particle. So the equivalent class of all the things that you can reach from one point to another is characterized by how many blacks you have.
Yeah.
And that's how you get the number of particles as a representative of the equivalent class.
Yeah, but in the case before, the one where you had the digits, right? This example here. Then here you have generated your data with only 4 different rotations. But when you calculate, did you do something similar here, updating your? You know, what the measure in this case would be. You would have to consider all the states with this in this rotation.
Yes.
4 rotation.
Yeah. The point is here. How do you find that the matrices are invariants of the thing? Yeah. I think here I did it that way because I knew already that this was the right thing. But you can show that. Yeah, these are the equivalent classes of the equivariant dynamics here also. Yeah. So, I mean, if you know what works, you can just do it. But if you don't know, and this is the point about normalization that I find interesting, like, if you don't know how to coarse grain, but you know the symmetry, you can extract the how to coarse grain from the symmetries. That is the orbits of the symmetry. Other questions?
So yeah, about these letters. Often you think of the symmetries that you want to capture as being continuous symmetries. Right? You would get sort of a continuous lattice, whatever that is. Like a locally infinite lattice, where intervals in the lattice are infinite.
I don't know, but the lattice is the lattice of subgroups, not you can have.
Right. Okay. Sure. Oh no. Only your coarse graining. That's true. Yes. That's good. So you still have a finite number of good.
Mm.
You may as well have on descriptions. Okay.
And just to finish, one thing that I've been doing lately is to now, so this is a story about prediction, but what I really want to do is about reinforcement learning. So how can you have an agent that is working with abstractions in order to plan when the phase space is too large? And here I have one example that I've been playing with that I call thermodynamic reinforcement learning, where you have the NFS situation, but now you have an agent that then can intervene on the particles. So the game is as follows. The agent can push particles between chambers. So at every time point, you can choose a particle and you push it to the other chamber. And there is some reward based on some chamber that is good. So at every time point, there is a light that tells the agent the first chamber is good. And then the agent starts pushing particles to the first chamber. And then at some point, the good chamber can switch. And then the agent say, oh, no, and then start pushing in the other direction. And that's the way it works. So what we see is here, just to make it easy, we have the agent can observe directly, no noise, or I don't remember if there's noise or not, but the point is that if you can have a micro agent that is learning the micro policy, so you see the whole thing and you're checking what happened if I push this particle here or there. So if you do vanilla reinforcement learning, you have a super gigantic lookup table, but you have to start populating the value function by trying different things. And long story short, if you do 40 particles, the microagent will never learn for the simple reason that we'll never see the microstate in the same configuration twice. Because there are as many states as the number of particles or whatever. Like if you have enough particles, the world, the configurations are so large that in a REL you need to try different things over the same state in order to see what happens. But if you never see the world twice in the same place, there's no way you can learn. So this is the micro agent. Then for 5 particles, they're pretty good. 8 particles, pretty good. 10, a bit less, and then 40 is that. Now, what can you do here with the coarse graining? You can have this macro agent that is just looking at is acting upon the number of particles. And in this case, I took a choice that is like the agent cannot see below the number of particles. So this is sort of a blind myopic agent. So because of that, it doesn't make sense also to have actions for every particle. So what I'm doing here is that the agent actually has 2 actions, push a random particle to the right or a random particle to the left. And now the control problem is much easier because it grows linearly with the number of particles instead of exponentially. And what happens is with 5 particles is a bit less good than the micro agent. And that happens because the way this simulation works is that the agent is blindly pushing one particle to the left or to the right. And when you have 5 particles and you have 4 in the good chamber and only 1 in the wrong one, this macro agent will push a random particle to the right and it will lose a lot of actions because it will be pushing the wrong particle very often. So it's a bit less good than the micro. But when you have 4 particles, the micro agent is still doing pretty good because it's learning a problem that is linear, so it's learnable and it does pretty decent. It's not optimal because of the same fact. Sometimes we'll push the wrong particles, but it's learning. While the other agent is absolutely not learning anything. So this is the direction I'm exploring right now. How can you use all these ideas of coarse graining in order to have efficient action? And this is going to be very related with how the reward function is defined. So there's a whole story about the reward function and how that reward tells you what is the right abstraction. And all of this is ongoing work. So to conclude, let me walk you some ideas. So to summarize, the first notion we saw was hierarchical emergence. This is about levels of systems with levels that are self-contained. And this is cool for 2 reasons. For the system itself, it allows controllability on its own at a simple way, and these levels of kind of internal logic to coexist. For the researcher, it's also useful because this is what allows to have effective theories that are perfect without any error, and also allows efficient simulation. Because if you know what are the levels, then you can tell, oh, I can simulate this level and forget about the things below. Second idea, word modeling. So word modeling is these auxiliary processes that help to explain and predict perception action loops. Key ideas is that for a given interface, you have many word models that are compatible. There is an intrinsic efficiency versus interpretability trade-off. And for agents that have to compute word models online, you have this optimal solution given by Bayesian belief updating. And finally, we found that the dynamical equivariance is a sufficient condition in order to guarantee some reflection of objective hierarchical emergence with subjective hierarchical belief updating. And this is cool because it allows exact Bayesian inference in very large systems. So you're not doing approximation. The trick is that you're not predicting everything. You're giving up on details, but what you're predicting often. So that's good. And this is and the hope is that this will lead to scalable approaches to RL in partially observed scenarios or in problems that are too large. With that, thank you for the attention.
Yeah, let's start with the question.
Yes. The examples you took, they are most, right? Because at the end, you have a dynamical process, when it goes towards the stationary, the thing you're measuring is like a stationary probability of being left or right, and so also the example in the Markov process is closed, right? So it's going to go towards a stationary state.
Yeah.
So did you do something like this with this course going on something that has no equilibrium? Or no stationary?
I haven't. I think you can do things, but it's going to be more complicated. But I think it's so. I think it can be extended, but I think the extension is not trivial. So yeah, very very interesting question, and I have not even thought about it. Also, there is a tricky thing. So, for example, in the case of the world model, you can have non-stationarity, but kind of stationary transitions. You know, they're like you can have and so that I think is pretty tractable. The full non-stationarity I think is very complicated. Any other questions?
So, I want to ask maybe something about this world model, the interface. So, in some sense, sort of the brain that's in the vat, or the AI that's in the vat, is doing the reverse thing, right? It's mapping something from the interface maps actions from that agent to what perceptions are we going to come back, and the agent is taking in perceptions and mapping it to actions.
Yep.
So is there maybe some duality in that, going from actions to perceptions or perceptions to actions?
Yeah, so
is there a way that this would help to understand better the AI that's in that?
Yeah, absolutely. So that very good question. So you can have the dual construction where the input is the observation and the output is the action, and the internal state is the internal state of the agent. And you can represent policies with that and agents, etc., etc. So a lot of people have tried to represent an agent environment interaction as coupled transducers. So basically, you have two transducers like this, and you put another one that you plug here. And you can have this alternation of things.
Yeah, right. Oh, yeah, that to include the.
Another thing you can do that is also interesting is that you can have multiple agents and they're sharing a single environment. And because you know the environment could contain other agents, and you can also model that. So yeah, all of that is possible. It's a bit what is hard in this story is how to be general and say something about it. You know, like it's a sort of a tricky question, especially when you go to the multi-agent case. You want to be fully general. It's so general that it's very hard to have conclusion or end up, you know, like. So, but that's one direction I'm thinking about. Like, how can you start studying multi-agent systems with this framework? And yeah, absolutely. It's a bit tricky. Like the question, I also feel a bit uncomfortable because, as you said, that imposes some symmetry between agents and environments, and I feel there is something wrong about that because I would like to think there is at least difference between agents and environments. And there is an old story about reversibility. People have always thought that agents are less reversible than environment, maybe, or there should be some statistical way to distinguish a passive environment from an active agent. But I've never seen somebody properly like doing something that is like, okay, that's right. You know, so there's the fit there is something there, but then nobody has been able to cash it out, I think. Not yet.
Yeah, interesting.
There was one talk about that at Iliad,
Mhm.
where they say we shouldn't align agents, we should align environment,
Nice.
which was nice. But we are the agents, like don't change us.
Uh,
Make sure that we're in a good environment.
right, nice.
Okay, do you have any more questions? If not, maybe let's thank the speaker again.